Hello everyone. Today I'm following up on a request from a viewer to talk about or show some examples of the precise definition of a limit or continuity, or when the definition doesn't work, that is when a limit does not exist or when a function is not continuous. I'm going to look at what is kind of like a standard example of a function not being continuous and use the epsilon definition formulation of continuity to show that this function is not continuous. So I've defined my function piecewise in terms of x. If x is rational, that is, if x can be written as a fraction of integers, then we set the value of the function equal to 1. If x is irrational, it cannot be written as a fraction, then we set the value of the function equal to 0. This is just the indicator function, or sometimes called the characteristic function, of the rationals. It might help to visualize what this function looks like. It's not really the easiest thing to visualize, but basically at the value 1 here, you have a whole bunch of like a cloud of points up here at all the rationals, but you also have a cloud of points down here at 0 whenever x is irrational. I don't know if this is the best way to draw it, but that'll do for now. And what we're going to do here is show that for any value of x, we're going to show that f is not continuous at any value of x. Okay, so first I'm going to write down the definition of continuity. That is, if we were trying to prove f is continuous, I'll write down what we would want to prove. And so if we want to prove that our function is not continuous at the point x0, what we would have to show is the following. Okay, so we want to show that there exists a delta positive such that for all positive delta, we can always find an x that is close to x naught, such that the difference between f of x and f of x naught is large, that is larger than epsilon. The way this is going to pan out, I will go through the argument logically, but the key here, the reason this works is because in any open interval of the reals, there will be both rationals and irrationals. And so for any open interval of the reals, there will be values of x that take on both 0 and 1 somewhere in there. So what we'll do is I'm going to let epsilon be equal to 1/2. That way, if x naught is rational, then the value of the function is 1. And we want to show that there's always going to be values of x. If we're taking a limit as, or if we're trying to show that this function is not continuous, I suppose it's kind of like this, right? If x is rational, like here, well, there's always going to be values of x. Wait, no, I have this backwards yet again. If x is rational, we want to show that there's always values of x within any interval around x naught, such that we're outside of this interval. So we're always going to be able to find a point here such that the value of the function there is 0, and that puts us outside this interval. On the other hand, if x is irrational, again, we can draw an interval like this. I'm going to take also a small interval around this point like that. There will be values of x in this interval such that the function evaluates up here which puts us outside this interval. Okay, so we have to do this in two parts. Suppose x naught is rational. In fact, before I do any of this, I know that epsilon over 2 will work in each case. Or epsilon equal 1 over 2 will work. So suppose x naught is rational, and let delta be arbitrary. Okay, well, there exists an x in this interval such that x is irrational, right? Any open interval will contain both rationals and irrationals. But what does that mean? We then have, let's write down f of x minus f of x naught. Okay, well, x is irrational, so f of x is 0, and f of x naught, because it's rational, is 1. So this equals 1, which is greater than epsilon. We do the exact same thing, but suppose that x naught is irrational. Again, let delta be positive and arbitrary. Well, there exists an x in the interval of concern, which is rational. So then f of x minus f of x naught will again be equal to 1, which is greater than epsilon. Yeah, that's it, really. This is kind of like the easiest. This is one of the easiest or most straightforward or common examples of showing that a function is not continuous anywhere. Is simply make sure that in any open interval, the function takes on values which are far apart from one another. Yeah, so that's it. I'm going to do one more example of using the epsilon delta formulation of continuity in discussing the properties, the continuity properties of some function. So stick around if you want to see that. Thanks for watching.